So to pick up with another example of the Biot-Savart law, we're going to look at the magnetic field due to a circular current loop. Now, for our circular current loop, I'm going to look at just the magnitude of the magnetic field from each little current element. So the magnitude means that I am just taking the absolute value of that ds crossed with r, the absolute value of that cross product. Now, if I look at what is happening, we are going to be looking at the magnetic field on the axis of a circular current loop. So just to highlight what that is, the axis of the loop is, in this example, the x-axis here. So if you were thinking of that current loop as like a wheel, you're thinking of the axis as like the axle of that wheel. Now we're going to define that this is x distance away from the center of the loop. So the center of the loop we're calling x equals 0. The other thing that's defined in this example is that the radius of the loop is this lowercase a. And we are carrying current in this example the way we're facing in a clockwise or counterclockwise direction. So using our right hand rule, we can curl our fingers in the direction of current and our thumb's going to point in the direction we would expect the magnetic field to be. Now for each little loop of current, you can see in our image here, we would expect with ds crossed with r, this little bit of current dB. And we're going to make an argument that with symmetry, the perpendicular portions of this cancel out, and the only thing we're going to be left with is the magnetic field along the axial direction, so along the x-axis. All right, so let's go to our math. When we do our first step, which is to evaluate that cross product, what we are going to get is just ds. So I'm going to get a mu 0 I over 4 pi, and over here I'm going to get a ds, and instead of r squared, I'm going to say a squared plus x squared. So remember, x is the point at which, it's the distance to the point at which we are evaluating our magnetic field from the origin or from the center of our circular current loop. A is the radius of the loop. So we've got this right triangle here that can help us write r in terms of two constants that we know of. All right, so that's our magnetic field in general. Our magnetic field in the x direction, we are going to make an argument for a similar triangle here as what is here, so that this angle theta is the same as this angle theta. Right? So I can write that the portion of my magnetic field that's in the axial or the x direction in this case is mu 0 times I over 4 pi. We've got ds a squared plus x squared. And then we've got cosine theta. So that cosine theta is just giving us this portion of the magnetic field, right? And dB was our hypotenuse, our overall portion of the total magnetic field from that little current element. So the axial magnetic field, we should just have to do an integral. So this is where the whole idea that this is a vector summation comes in. I am just adding the x components right now, because to add the overall dBs, they all point in different directions, so I need to break them down into their components. I can make the argument that the perpendicular ones cancel out, that there's a mirror image down here, another ds that's going to have the opposite perpendicular one, but a similar axial one. Okay, so To do that, I want to rearrange some of my information. So I want to take this cosine theta and rewrite it in terms of this triangle that I have, this larger triangle with A and X and R. So I can rewrite my cosine as my adjacent side over my hypotenuse. And remember, my hypotenuse is just going to be an A squared plus X squared, and then I'm going to take the square root of that, right? So that is my adjacent side over my hypotenuse. So I'm going to substitute that in this integral. When I do that, I have an integral that looks like mu 0 I 4 pi ds a squared plus x squared times a over a squared plus x squared to the 1/2, right? So I can begin to simplify this, and really this integral, I am going to go around the whole loop of ds. So everything in this integral is a constant except for ds. And if I'm going to integrate around that whole loop, I'm really just going around a circle. So if I start to combine things that look alike, I've got an a on top here. I've got a squared plus x to the 1 power and a squared plus x to the 1/2 power. You just add powers together when you multiply those things. So a squared plus x squared to the 3/2 power on the bottom there. And when we do that integral around all of ds, we're just going to go around the circumference. So we're going to go around 2 pi a circumference of this object. Okay, so some 2's cancel, the 2 and the 4 partially cancel, the pi's cancel, and we end up with our final answer for this magnetic field on the axis of a current loop. So after doing the integral around the whole circumference of the current loop, which is 2 pi a, we end up with this relationship. Now we can cancel some things out, and we get that on the axis of our current loop, we've got mu 0 I a squared over 2 times a squared plus x squared plus x squared. Let's make that neater. And this is to the 3/2 power. So that's kind of interesting. And that is the overall magnetic field. So as long as we're on the axis of the current loop, these perpendicular parts of the field cancel out. So the subscript x is just letting us know that it is going in that axial direction. And we can double check that again with the right-hand rule. At the center of the loop, remember I said that was a point we defined as x equals 0, right? So at the center of the loop, our magnetic field looks like mu 0 times I. X equals 0, so this bottom part becomes 2a squared to the 3/2 power. That simplifies to 2a to the 3rd, right? So that's at the center of the loop, the magnetic field strength. Oh, sorry, I dropped an a squared there. So let's redo that. the center of the loop, we've got mu 0 I a squared on the top and then 2a to the third on the bottom, which gets us to mu 0 I over 2a as our field strength at the center of the loop. That makes a lot more sense to me. Pause there because it didn't look right to me. Glad I found my error. All right, so that's at the center of the loop. Very far away, let's look at very far away. So if our axial field strength looks like this in general, so mu 0 I a squared over 2 times the quantity a squared plus x squared to the 3/2 power. If our axial magnetic field looks like that, then when we are very far away, but still on that axis, so we're still on the axis x, but we're really, really far away so that this looks really tiny. Our radius of our loop looks really tiny compared to how far away we are. Our magnetic field can be thought of as approximately mu 0 I times a squared. And the quantity x squared would be so close to x squared plus a squared because they are so, a squared is so small that you would have 2x to the third there on the bottom. This can actually be thought of in terms of the dipole moment of our loop. So remember, dipole moment is our current times the area that's described by that current loop, right? So this is the area that's described. And mu is our dipole moment of the loop. So this magnetic field, when we get really far away, is approximately mu 0 times mu, which remember is our dipole moment and our permeability of free space, over 2x to the third. So it drops off by x to the third when we're looking at a current loop. Okay, this is a good place to pause and talk about the magnetic field on the axis of a circular current loop a little further, and then move on to some other applications.